So the lady does not object. Very kind of her. Our speaker is Professor Manuilov Vladimir Markovich, of Moscow University. In which language he will speak, we shall see now. But as it is a rule, he is writing in English. So with pleasure, I give him the word. Пожалуйста, Vladimir Markovich.
Thank you very much for inviting me to give a talk. And if the talk was announced in English, so I think that I should speak English.
Okay, we are pleased.
Okay, so the topic of my talk is related to the so-called row algebra. Row algebra is quite an interesting object. It is a sister algebra which is related to metric properties of spaces, and especially it reflects behavior at infinity for spaces. So this is interesting, for example, for discrete groups with the word length metric and similar spaces. And the origin, row algebras were defined by John Rowe, who was a student of Atiyah, and in relation to pseudo-differential operators and index theory. So this is the sister algebra where pseudo-differential operators live. Okay, so let me begin with some basic definitions. So we start with a locally compact metric space and a Hilbert space, which are related by an action pi of the algebra of functions, continuous functions on X, which vanish at infinity. And we shall write standardly B of H and K of H for the bounded or compact operators on the Hilbert space H. To define the row algebra, we need two properties. That we need that this action pi should satisfy the two properties, which are labeled here by 1 and 2. The first means that the image of pi is quite big, so that the elements of this form pi of f times xi are dense in this Hilbert space. And another requirement is that if pi of some function f is a compact operator, then this should imply that the function is 0. So all functions are mapped into something non-compact. If these are satisfied, then one can define
is greater than okay, so that's finite. There exists some
R. An operator T is called locally compact if its product is two products, the right side and the left side product with pi of any function f are compact, and it has finite propagation if the product pi of some function f t pi of some other function g vanishes whenever the distance between the supports of functions f and g is greater than some number r. So these properties really reflect the behavior or pseudo-differential operators. And we may complete the set of such operators with respect to the norm on this Hilbert space, and the result is the row algebra. There is a theorem saying that this construction doesn't depend on the choice of the space Hx if it satisfies the two properties from the previous page. Sorry. Sorry, I'm afraid that I don't see the upper line. Okay. Sorry. Okay. So, sorry for technical problems. When the space is discrete, when the space is not discrete and it has some nice measure, then it's possible to consider the natural action of the functions on the space X on the Hilbert space L2 of X. This holds when the measure on X has no atoms, but if it has, then one has to do something about the property 2 from the previous page. So if we have atoms, then this doesn't hold. The delta function of an atom is compact and the function is not trivial. So when a space is discrete, then this choice of L2 of X will not satisfy this condition. So we may take, for example, the tensor product of L2 of X times some infinite dimensional Hilbert space. Then we get this row algebra of the discrete space X. But there is also another option. We can still use the same small Hilbert space L2 of X without tensoring it by something infinite dimension. And the resulting sister algebra will be smaller. It differs from the row algebra, and it is called uniform row algebra of X. Calculations are more easy with this sister algebra, but it is quite far from the elliptic theory of pseudo-differential operators, which was the main idea why to study this row algebra. Okay, manifolds and some other spaces are often endowed with discrete subspaces, which are tens in some sense. For example, lattices in Lie groups, or more generally, Delone sets in metric spaces. Some problems related to the space X may become simpler when reduced to such a discretization D. In particular, it would be interesting to understand the relation between the row algebra of X and the uniform row algebras of its discretizations. The latter are embedded, of course, into the row algebra of X, and we have shown, for example, that a large class of non-trivial projections in the uniform row algebra of the discretization may vanish in the K-theory of the full row algebra. But the Delone sets on general metric spaces are too general to deal with, and so we have to restrict to something more regular. And here I will speak about the case when X is a simplicial complex. Just a space which consists of simplices, and the set of vertices will be a discretization of X. And if we want to get more and more dense discretizations, we shall divide the simplices of X into smaller simplices. Okay, so let X be such a simplicial space. We shall restrict our we shall put several restrictions. For example, we want that this space is uniformly locally bounded, which means that each simplex had not too many adjacent simplices. The number of adjacent simplices is uniformly bounded, and also the dimension of simplices is also uniformly bounded. Simplices, some simplices have maximal dimension if they are not a subset of a greater simplex. For example, it is allowed to have simplices of different maximal dimensions. For example, we can add a segment to a triangle. This is okay. We have to introduce some metric, and let us do it as follows. We assume that each simplex is isometric to the standard simplex, which is given by these equations in the Euclidean space. And we can take the measure and the metric from this standard simplex. And if 2 points are placed on different simplices, then we can define the distance between them by an infimum of all possible distances of all possible ways from one point to another. Within each simplex, the distance is the standard one. Okay, so we can use the standard coordinates on the simplices as well. So for this simplicial structure, we can take the set D, which we will write as D1 as a set of all vertices. If the size of each simplex is standard, so each edge has length 1, then this is at least one net for X, for the space X. Our assumptions imply also that this discretization has the so-called bounded geometry, which means that the number of points of any ball of radius r in this space is bounded by some number b of r, which depends only on r, but not on the center of the ball. This condition is quite useful in study of metric spaces at infinity. Then we divide each simplex into equal smaller simplices of size twice smaller than the original one, and get the next discretization D2, which consists of the similar simplices, but the distance between the lengths of the edges will be 1/2. And then we proceed infinitely and obtain more and more dense discretizations with the lengths of edges of the simplices equal to 2 to the power minus n. Okay, so we shall get something like this picture. So we have a big simplex, which can be divided into 4 smaller simplices, and then into, I don't know how many, even lesser, twice lesser simplices, and so on. Let us denote the open star of a vertex u by st sub u. Then the star means that we consider all simplices which contain this point, except the boundary, of course. And now we shall need something like a partition of unity. So we take not an arbitrary partition of unity, but a quite special one, which consists of piecewise linear functions, which equal 1 at u and 0 outside the star of u. So, for example, if some point has such coordinates and the standard such standard coordinates, then this function equals to the corresponding coordinate. And thus we have a set of functions which each of which equals 1 at the corresponding vertex and 0 at other vertices. And of course, the scalar product of such two functions vanish only when the vertices are far away. If they are close to each other, then the inner product is non-zero. And we can form the Gramian or the Gram matrix for this set of functions. As we have this standard basis on the small L2, so we can think of this Gram matrix as a matrix of an operator, of some operator. And the norm, well, infinite matrices do not determine bounded operators in general, but this one does because of our condition of bounded geometry. Roughly speaking, bounded geometry means that this infinite matrix has not more than a finite number of diagonals, not non-zero diagonals. That's why this matrix determines a bounded operator. But also this operator is positive, patently because it's a Gram matrix. But there is no guarantee that this operator is bounded from below, from 0. And this is the first result, which can be checked by an exercise in calculus, in multiple integration, which shows that which shows that really this operator is bounded from below. So it determines an invertible operator. And that's the point. So it can be inverted. The the inverse operator is also bounded. And also it has finite propagation because operators of finite propagation are norm closed. So when we take the inverse, it can be written as a series, and that's why also has finite propagation. I mean, lies, well, formally it's not, well, G, of course, is of finite propagation, but the inverse also will be the limit of operators of finite propagation. And now we can define maps from, well, maybe I say some words about the idea behind this. The idea is the following. The partition of unity, or any partition of unity, is not orthogonal. The inner products are non-zero, typically. And of course, we can apply the Gram-Schmidt orthogonalization to get an orthogonal basis or orthogonal system of functions. But the transition matrix from the original, from the functions of the partition of unity to this orthogonal basis will be not of finite propagation if we use the Gram-Schmidt orthogonalization. And I want it to have finite propagation too. So that's the way we take the square root of the gram matrix and use the inverse of the square root as a transition matrix, as a transition matrix. So we get an orthonormal system of functions, psi sub u, which is obtained from partition of unity by this matrix C, which is the inverse of the square root of the Gramian. And because of this invertibility of the Gramian, we can define a map from the small L2 of the discretization to the row algebra of the whole space. We can map delta functions of vertices to the corresponding functions psi sub u, which are already orthogonal. So psi is an orthonormal basis. That's why this u is an isometry. And we can define a map from the uniform row algebra of the discretization to the row algebra of X just by standardly by u, t, u star using this isometry. And, because of our choice of orthogonalization as an inverse of the square root of the Gramian, the result is not just an operator on L2 of X, but it has finite propagation, or at least a limit of operators of finite propagation. And this alpha is patently a star homomorphism, so it defines an inclusion of the uniform row algebra of D into the row algebra of X. Okay. Similarly, we can use the same isometry to obtain a map in the backward direction, but it will be not a star homomorphism. It will be just a completely positive map, which also is useful, but not as nice as the map alpha. So this completely positive map is denoted by beta here. And this can be done for each discretization, for each number n. And we get the sequence of maps alpha sub n, beta sub n, and everything else can be numbered by this n. So let me recall that a continuous field of sister algebras, or bundle of sister algebras, or C of T sister algebras were introduced by Fell, and it is a triple consisting of a space T, of a sister algebra A, and of projections pi sub T from A to A sub T. So these quotient maps should be surjective. The family pi sub T should be faithful, and most important is that the map from T to the norm of P sub T of A should be continuous for any element of sister algebra A. So in our case, we shall use the quite simple space T, which will be integers and infinity. Each AN will be the uniform row algebra of nth discretization, and A sub infinity will be the row algebra of the whole space X. And then we can construct the sister algebra A as a subalgebra of the product of all A sub t. Let me denote by J the set of vanishing at infinity sequences. So it was just a direct sum of these A sub t. And let B be the functions B sub t of S, where S is an element of the row algebra of X. So both are subalgebras of this f of t, and we can take the sum. It's not a direct sum, it's just a sum, the set of all possible sums, and it turns out that it is norm-closed, and it gives a continuous field of sister algebras. Continuous fields are usually used to relate K-theory of the limit point, like here the infinity point, to the K-theory of finite points. So I will speak about this later. But the next relation between, so this was the first relation between the sister algebras of discretizations and the row algebra of the limit space. And another relation is given by the direct limit. In fact, we have constructed maps alpha sub n from the uniform row algebras of discretizations to the row algebra of X. And of course, well, the problem is that the natural inclusion of d sub n is a subset of d sub n plus 1. And this inclusion, of course, induces an inclusion of sister algebras. But this triangle, if J is given by the inclusion, it doesn't commute. So this is the problem. We cannot pass to the direct limit. But using this orthonormal basis psi sub u, it is possible to find another map from nth discretization to n plus 1s, to n plus 1 discretization, which will make this diagram commute indeed. So recall that Hn is the closed subspace of L2 of X, which is spanned by our partition of unity. And this partition of unity is, although it is not orthonormal, but still it's some quite reasonably nice basis for this space. When we consider the inclusion of this H sub n to H sub n plus 1, then it's quite easy to see that the partition of unity, because it was piecewise linear, it can be written as the corresponding function of the partition of unity with the number n plus 1 plus some functions of the same partition of unity centered at nearby vertices. So X should be nearby this U, and this linear combination gives the function phi sub u with the number n. So we take the sum over all x which lie in the same simplex. And this formula number 5, determines an inclusion of H sub n into H sub n plus 1. and we can use this inclusion to relate. Well, in fact, it suffices to use this inclusion to construct this map J sub n. So we can write this by formulas. So we can define W sub n as a product U sub n, then the identity on n, and then U star sub n plus 1. And so this Wn is an isometry. It is completely different from the isometry induced by the inclusion of dn into dn plus 1. And we can define this J sub n as a W times T times W star. So this J sub n gives a star homomorphism. And of course, we have to check that if we apply this J sub n to a finite propagation operator, we get also a finite propagation operator, but this is quite easy. And then we get a map. First of all, we get a direct limit of these uniform row algebras of discretizations, and we get it together with a map into the row algebra of the whole X. So we get this map. It is interesting to describe the image of this alpha. So to describe which operators of finite propagation in C star of X in the row algebra of X can be obtained from the similar operators of discretizations. So to do that, I would like to describe a picture of the row algebra of X in another terms similar to those for uniform row algebras. The idea is that if we cut X into pieces centered at the vertices, at the points of discretizations, then we can, that we can divide the whole X into sets F sub U, such that X is their union, and the measure of intersections is 0. And these sets are not very far. F sub U should be not very far from the point U. It should be somewhere between a small ball and a large ball centered at the same point U. Then the whole space L2 of X is the direct sum of these smaller Hilbert spaces which are located near the vertices. And then if we write an operator as a matrix, then this operator will be of finite propagation and locally compact if each entry T sub UV is compact for any U and V. And also the condition of finite propagations remains. So we can think about elements of the row algebra of X as infinite matrices with compact entries and located, non-trivial entries are located near the diagonal. Well, we can consider the subset of operators of special form, namely of propagation smaller than some L. And also we require that the rank of the matrix entries T sub uv does not exceed some number m for any u and v. So if we have two operators with satisfying these two conditions, so first the propagation is bounded by L and the rank is bounded by M, then the product will be of the similar form, but with different numbers. The M and L will be replaced by M times B of L and B of L, where B of L denotes the maximal size, the maximal number of points in the ball of radius L. And that's why the union of all these R sub ML of X is a star subalgebra in the row algebra of X. And we can pass to the closure, and the result will be some C star subalgebra of the row algebra. And clearly, the image of alpha of our direct limit of the uniform algebras of X lie in this R of X. So my conjecture is that, in fact, it coincides with this R of X, but I don't know how to prove this. At least it is very similar to this R of X. And this R of X can be viewed as a right definition for the uniform row algebra of non-discrete spaces. So the uniform row algebras were defined only for discrete spaces, and this way allows us to define something for non-discrete spaces, which behaves like the uniform row algebra. Okay, and now a few words about K-theory. So as I mentioned, the continuous fields of C-star algebras induce some maps in K-theory. For example, if some operator is a projection, then, which means that it satisfies C equals C star equals C squared, then the limit of the maps beta sub n of S squared minus beta sub n of S, which is just a beta infinity, which is just simply S itself. So it is S squared minus S, and since S is a projection, it vanishes. So beta sub n of S is what is called an almost projection when n is sufficiently great, which means that the norm of its square minus itself is small, which allows to find a genuine projection close to this beta sub n of S. So although it is only an almost projection, not genuine projection, it still determines some class in the K-theory. Similarly, it works for unitaries and the group K1. So projections correspond to K0 and unitaries correspond to K1. And the same idea still works. If something is close to unitary, then there exists a unitary nearby. So this gives a map from the K-theory of the fiber over the limit point of the continuous field of C-star algebras to K-theory of the points before taking the limit. So the inclusion, of course, induces a mapping K-theory in the opposite direction. And of course, it's interesting to evaluate the compositions of these two maps for general spaces. But this is quite difficult problem. But what I can do is to consider the simplest non-trivial case when X is real numbers. In this case, everything can be calculated. We have discretizations just by points of the lattices of integers. We take lattices which become more and more dense, and there is an explicit description of the generator of K1 of the row algebra of the real line. It is, I think it was John Rowe himself who calculated this generator. The K1 group of this row algebra is just integers, so it has only one generator. It can be written explicitly, as I mentioned, and we can calculate its image in the K-theory of uniform row algebras of the lattice of the integers. And in fact, K-theory of the uniform row algebra is much bigger than the K-theory of the row algebra, the full row algebra, because many non-equivalent projections become equivalent in the bigger sister algebra. So it's maybe not quite usual way of behavior, but I mean, when we embed a smaller sister algebra into the bigger one, then a K-theory becomes much smaller because many projections and many unitaries which were not equivalent, they become equivalent now. And the result is that this composition, when we take beta and then alpha, is the identity map on the K1 of the full row algebra of the real line. Well, so I think that I haven't followed the clock, and I'm afraid that I have told you all I want.
Okay. No, it was 45 minutes, but because it was very, stuffed matter, so I think we must be satisfied. Yes. So you have finished, Vladimir.
Yes.
So
Yes.
thank you very much. Indeed, it was very interesting. And now questions.
Please.
Gentlemen.
Yes, can I have a question, please?
Okay.
Well, in your definition, when you want to try to pass the inductive limit, your subspaces Hn, are they finite dimensional, right? As far as I understood.
No, they are infinite. Formally, they can be finite dimensional if the space X has bounded radius, but this is not very interesting. Usually, this theory is about spaces of infinite radius, infinite diameter, and otherwise everything reduces to compact operators. If the space is of
that's
finite.
right. So it's not allowed for you to have compact operators for CU, right? For row algebra.
Yeah.
So that's why but you had a matrices somewhere, and after some step you passed to infinite dimensional. I didn't get it properly, so that's the point. So matrices, they're not allowed for use, I guess, right? For your row algebras. And
maybe I'll give some example. Let me.
Yeah.
Let me draw a picture. So this may be the simplest example when X is just real numbers. We have a discretization here.
Mhm.
So we have these are functions phi u. They have this form, and this space H sub n is the linear span
Mhm.
of the
Yeah.
closure of these phi u in 1/2 to the power n z. So
Ah.
this space H sub n is infinite dimensional in this example and in most other interesting non-trivial cases. And the problem was how to embed it into n plus H sub n plus 1 when we divide each interval into 2 parts and get some smaller functions.
Ah,
Uh,
see. Mhm. I see, yes.
Okay, other questions?
Okay, yes, thanks.
Yes. Okay. Now, so again, let us thank our speaker for indeed a very interesting talk. Yes, we shall meet some of us after a week, and the speaker will be Piotr Raldovich Ivankov, yes, whom we have heard several times. Yes, so I hope everybody will be present. So bye-bye, thank you. Thanks for all.
Thank you. Thank
Yeah.
you.
Thank
very
you.
much.
Thank you. Bye-bye.
Bye.
До свидания.
Вот, до свидания.
До свидания.